This is a control room inside an industrial facility. Architecturally, the space is shaped by an elliptical plan and a dominant, curved, exposed concrete ceiling. A control room is not just a room with screens and chairs. It's a space where people have to listen carefully, stay focused for long hours, and make critical decisions based on sound. When the acoustics are wrong, the problem is not just discomfort. It's fatigue, miscommunication, and loss of clarity. Now imagine this control room inside an elliptical space, with a hard concrete ceiling and strong architectural character. From an acoustic point of view, this is where things get complicated. This project is not about creating a perfect laboratory environment. It's about understanding what actually happens to sound in a real space, and deciding how far we should intervene and where we should not. Unlike many public spaces, the goal here is not loudness or impact. The goal is clarity, comfort, and consistency throughout the day. Every surface in the room plays a role. The walls, the ceiling, even the overall shape of the space influence how sound travels, reflects, and builds up. In a control room, sound should feel natural and predictable. Voices should be easy to understand without effort, and the room should never become tiring to listen to. That's why acoustic design in spaces like this is not about adding treatments everywhere. It's about understanding how the room behaves, and guiding sound rather than fighting it. Before proposing any acoustic treatment, we first needed to understand how the room actually behaves. Not by assumption, and not only by experience, but through simulation. The raw space was modeled using its real geometry and materials. An elliptical plan, hard reflective surfaces, and a continuous exposed concrete ceiling. The purpose of this simulation was not to chase exact numbers, but to reveal patterns in how sound energy moves, reflects, and decays inside the room. The results showed that sound in this space does not fade in a smooth or balanced way. Reverberation is uneven, with a noticeable amount of late energy building up, especially beneath the curved ceiling. This means that sound remains in the room longer than desirable, gradually reducing clarity and increasing listening effort over long working hours. When we looked at speech-related indicators, the same behavior appeared from another angle. Instead of a clear separation between direct sound and reflections, the room produces overlapping reflections that mask speech and blur definition. Clarity is inconsistent across the space, not because of a single problematic surface, but because the geometry itself is guiding sound toward certain areas. The elliptical form acts almost like an acoustic lens, concentrating energy rather than distributing it evenly. The simulation revealed distinct focusing zones where sound pressure builds up, while other areas remain acoustically weaker. One important thing needs to be clarified about this project. The elliptical form of the room is not an accident. It is not a mistake. And it is not something that was left unresolved. It is a deliberate, architectural decision, and a clear requirement from the client. From a purely acoustic perspective, removing or reshaping this form would have been the simplest solution. But real projects are not solved by eliminating constraints. Our goal was never to turn this space into a laboratory. The real challenge was different: to improve acoustic performance without erasing the character of the space. In this project, the form is not treated as an obstacle to fight against, but as a condition to understand, respect, and work with. The first acoustic intervention in this space was not absorption. It was geometry. Instead of immediately removing sound energy, we introduced a new architectural layer: ceiling louvers. Their purpose was not to silence the room, but to change how sound moves within it. In a space defined by an elliptical plan and a curved concrete ceiling, sound tends to travel uninterrupted, forming long reflection paths and zones of acoustic focus. The louvers were designed to interrupt those paths to break continuity without erasing the character of the space. Once introduced, reflections were no longer smooth or predictable. They became fragmented, redirected, and distributed across time and space. This created what can be described as a coarse level of energy control, a geometric reshaping of sound behavior before any fine acoustic tuning takes place. Simulation clearly revealed this shift. Dominant early reflections were reduced, sound energy became more evenly distributed, and speech-related clarity indicators showed noticeable improvement. At the same time, overall reverberation remained relatively high. It was an expected outcome. Louvers reshape sound. They do not remove it. Geometric control alone does not remove sound energy from a space. It reshapes reflections, but it does not shorten their lifespan. To actively reduce stored acoustic energy, absorption had to be introduced deliberately and selectively. The most critical locations were the wall-ceiling junctions and the room's perimeter, where late field sound energy naturally accumulates. These areas are especially influential in the mid-frequency range, the range most critical to speech intelligibility, listening effort, and cognitive fatigue. High-performance absorbers were therefore integrated along these boundaries, designed specifically to target mid-frequency energy. The intention was not to deaden the room, nor to rely on superficial treatments, but to remove the energy that most directly interferes with clarity and decision-making. At this stage, the design moved beyond shaping sound paths and into shaping the acoustic response itself, from geometry to physics. Simulation clearly revealed the impact of this intervention. Late arriving energy was significantly reduced, overall reverberation began to decay more evenly, and speech-related clarity indicators showed measurable improvement throughout the space. At the same time, reverberation was not eliminated. The room retained acoustic presence while gaining control, but this was not the end of the process. A closer examination of the results revealed a new challenge. In certain frequency bands, acoustic energy had been reduced too aggressively, while other parameters had not yet reached a balanced state. As a result, parts of the space began to sound overly dry, even though the overall acoustic control was still incomplete across the full spectrum. This marks the point where acoustics moves beyond predefined solutions and enters a phase of fine-tuning. In response, nearly 50% of the perimeter absorbers were deliberately removed. This was not a rollback, but a refinement. The earlier perimeter treatment had been effective in reducing late reflections, but it also contributed to localized overdamping and spatial inconsistency. By reducing this coverage, excess absorption in the near field was relieved, allowing energy to redistribute more evenly throughout the room. At the same time, part of the concrete ceiling, specifically the zones located between the louvers, was converted into targeted absorptive surfaces. These absorbers were designed with a controlled frequency response, focusing primarily on problematic mid-range frequencies that affect intelligibility, listening effort, and long-term acoustic comfort. Rather than absorbing broadly, they intervened precisely where reflections were most disruptive in time and frequency. Importantly, the central areas of the ceiling were intentionally kept exposed. The exposed concrete ceiling was a clear architectural requirement from the client, and instead of treating it as a limitation, it was reframed as an opportunity. By preserving these reflective zones, spatial depth and acoustic presence were maintained, preventing the room from becoming perceptually flat or acoustically lifeless. This redistribution of absorption led to measurable changes in acoustic quantities. Mid-frequency decay times became more balanced, clarity stabilized across listening positions, and the contrast between overly dry zones and uncontrolled areas was reduced. The room no longer behaved as a collection of isolated acoustic conditions, but as a more coherent system. Final furnishings were introduced at this stage as well, contributing subtle absorption and diffusion that further smoothed the response without dominating it. Together, these adjustments mark a transition into true fine-tuning, where the goal is no longer maximum reduction, but controlled balance. Here, acoustic design demonstrates its maturity, understanding that more treatment is not always better, and that precision often achieves more than excess. This project represents decision-making in real conditions, not idealized ones. It shows how acoustic performance, architectural intent, and functional requirements must work together, rather than compete with each other. Here, improvement did not come from doing more, but from understanding better. From recognizing limits, questioning results, and turning constraints into opportunities. In the end, the goal was not acoustic perfection, but a balanced space, engineered, intentional, and true to its character.